In a previous video, we discussed diffraction from a general object, and I demonstrated how the diffraction pattern from a general object was given by a Fourier transform of the object off which the incident rays scatter. What we want to consider now is what effect that has when we then, our general object is actually a crystal, something with this translational periodicity that we described in one of the crystallography videos. So if we have a crystal, now what we can think of is rather than having our general object, we could break it up into the small unit cells. So each of our unit cells we could describe as some sort of electron density for the cell, convoluted with a position defined by each of these cells, because we can say that each of the cells just relates by a translational periodicity. So we can see here what we've got is this is just a mathematical definition for our lattice. So all we're defining here is the electron density for the cell, and we're putting it at each of the points of the lattice. So this is the same as basically saying we've got our structural motif and we're putting it at each of the points of the lattice. Now what we can think of is if we've defined our scattering as the Fourier transform of this, we could then take the Fourier transform of this function that we have here. So the Fourier transform of this, now if you're not mathematically inclined, don't worry too much about this, but basically the Fourier transform of two things convoluted together through convolution theorem we could show as the Fourier transform of one multiplied by the Fourier transform of the other. And so what we get is the Fourier transform of the cell, which defines something that we call the structure factor, and then the Fourier transform of this lattice. And this is the key thing here, is we've got this Fourier transform of the lattice, which gives us, when we work it out mathematically, this expression here. So we've said that our diffraction from our crystal is equal to the structure factor multiplied by the Fourier transform of this lattice, which gives us this term that we show here. Now what it turns out is that mathematically this triple sum is only significant if the exponent of this exponential of this term here is a multiple of 2 pi. And in turn what that means is, to get a multiple of 2 pi, this part of the expression here, the n1a plus n2b plus n3c dot s, must be an integer. And consequently what that means is that this will only be significant and will only get scattering if this is restricted to a series of points defined by this expression here. And this defines the so-called reciprocal lattice of the material. And you can do the full derivation and show that mathematically and work that out as we've done here. Another way of saying it, just thinking about it more in terms of implication, is if we have a lattice and do the Fourier transform of the lattice, it turns out that the Fourier transform of a lattice is in itself a lattice that is defined by a series of reciprocal lattice vectors. So you can see here I've got this lattice that I'm defining. We can see that this is a definition of a lattice here. We've got a series of 3 lattice vectors, A star, B star, and C star, and we're saying that we've got some unit integer combination of those which defines any point in this structure. So this defines our so-called reciprocal lattice. So scattering is therefore produced as a series of discrete points. And this is the key thing that, for example, Lowy and the Braggs noticed, is that if we have a crystal, our diffraction pattern is a series of distinct key points. We get a series of sharp diffraction maxima in that diffraction pattern. And this is the key thing here. So we've got this reciprocal lattice, and actually we've got these reciprocal lattice vectors, as I called them, A star, B star, and C star, and it turns out we can relate those to the real space lattice vectors as A star is equal to B cross C divided by V, which is the volume of the unit cell, and similarly B star and C star. And that gives a very key mathematical relationship here, because if we were to take A star and do the dot product of that with A, we just end up with 1. If we do A star and dot it with either B or C, we're just going to get 0. And that means that if you go back to this expression here, you can start to see that if we're doing A dotted with this, we're going to get certain terms cancelling out within that expression, and we're only going to get certain terms left. And so what this means is that my diffraction is restricted to certain key spots, and so we get discrete diffracted beams produced by diffraction from a crystal. And that can be defined by my reciprocal lattice shown here. And so here I've got a picture of my reciprocal lattice, and where I've got these points, I would get diffraction occurring. Now notice that these diffraction spots I've defined with these reciprocal lattice vectors A star, B star, and C star, and they're given by this nomenclature 1, 0, 0 with curved brackets here. Now that is because, as you see here, we've labelled this as H, K, and L. These are my integers of my reciprocal lattice vectors H, K, and L, but they are also defining a plane. This 1, 0, 0 is defining the 1, 0, 0 planes off which I am getting diffraction occurring in order to produce that diffraction spot. So this diffraction spot here is being produced by diffraction occurring off my 1, 0, 0 planes in my crystal structure. This diffraction spot here is being produced by my 0, 1, 0 planes within my crystal structure. This diffraction spot here, which would be my 1, 1, 0 in terms of HKLs, is therefore being produced by diffraction off the 1, 1, 0 planes within the crystal structure. So this is why we've used this Miller indices way of describing it, because actually it turns out we can relate this to what we see in the reciprocal lattice. So having this HKL reciprocal relationship where we said it was the intercept was A over H, B over K, C over L. It turns out mathematically it all comes together here because we're then seeing these diffraction spots that are being produced by those specific planes that we have in our crystal structure there. So if we have a crystal, what we have now shown is that we're going to get diffraction restricted to key points that are defined by the reciprocal lattice. So a crystal structure will produce a diffraction pattern that has a diffraction only in certain certain discrete spots, certain discrete diffraction beams, which we can define by the reciprocal lattice shown here.